Okay, so problem 13, indicate what types of reactions each of the following represents. Okay, so um, there are two or maybe three types of reactions that we want to be aware of. Um, the first reaction that we kind of already have discussed a little bit is the metathesis reaction, right? Do you remember what A, B, and C, D represent in this type of a reaction?
Um, they represent ionic compounds, aqueous ionic compounds.
That's right, ionic compounds that are aqueous. And when they're aqueous, they separate into their substituents. So if I were to write the ionic equation for this type of a metathesis or metathesis reaction, um, they would break up into their ions, and then they would form new compounds where the cation of one would go with the cation of the other. And then C and B would go together as well, right? So this is one type of a reaction. The other type, and so you can find it and recognize it by just looking and seeing two ionic compounds to start off with, and then they come together and they form different ionic compounds. In the ionic equation, so this is what we call the molecular equation, even though it has nothing to do with molecules. And this one is the ionic equation. In the ionic equation here, this is AD plus CB. The two of these ions are generally going to be ionized, and one is going to be a solid. It forms a precipitate, or maybe it's a liquid like water. Okay? So that's one type of a reaction. Follows that pattern. Let me give you an example of one. Sodium chloride plus silver nitrate. These are both ionic compounds that are aqueous. And the products are sodium going with the nitrate. And what do you think the other product is?
Um, silver going with the chloride.
That's right, silver going with the chloride. And we can look at our solubility rules and see that they identify chlorides as generally soluble, but silver chloride is an exception. Silver chloride is an exception. So what does that mean here?
Well, that's going to be solid.
That's right, it's solid. It's not soluble when it goes into water. This one is soluble. That's one example. Another example of these metathesis reactions, another example would be an acid combining with a base following the same form, A, B, C, D, and we get H2O and NaOH, right? No, sorry, NaCl, NaCl. Okay, all right, so it follows that same pattern. The other kind of reaction is what we call a redox reaction. And you identify the redox reaction by looking at the oxidation state, oxidation number of the different elements within the reactant or product. So, do you remember how to identify the different elements within the a different oxidation number of the elements?
Kind of. We talked about it, right?
Yeah. So what is the oxidation number for, like looking at A here? What's the oxidation number for the calcium?
Elements by themselves, it's just zero.
That's right. It's just zero. And so here's bromine. It's also zero. But here we see it coming together, and now in this compound, the oxidation number for calcium is different than it was over here. On the left it's zero, but over here now it has a +2 charge. And the charge on monatomic ions is the oxidation number. So if it goes from 0 to what?
+2.
That's right. And if it goes from calcium, 0, to calcium +2, that has it gained electrons or lost electrons?
The +2. No. It lost electrons.
That's right, it loses the electrons, loses those 2 electrons. Okay? Bromine, Br2, going to 2 of these Br minus ions, right? Is that gained? Have each of these gained an electron or lost?
It gained, each one gained 1, so there's 2 electrons.
2 electrons were gained, weren't they? So, do you remember what you call it when you lose electrons?
It's oil rig, right?
Oil. So what does oil stand for?
Loss. Oxidation is loss.
Okay, so I'll write that up here real quick. Oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. Okay? So, this is an oxidative half reaction, and this is a reductive half reaction. So you can tell that A is a redox reaction because it doesn't follow this metathesis pattern. How about C here?
Is that following the pattern?
It doesn't look like it, does it?
So we have to check the oxidation numbers?
Yeah, we have to check the oxidation numbers. So C6H12. Do you know the oxidation number for the hydrogens and the carbons?
The hydrogen's +1, right?
Hydrogens +1. So all of these contribute a total of +12 because there's 12 of those hydrogens. That means carbon, if there's 6 of those, each one must be a -2. But if we look at the other side of the equation, in the form of carbon dioxide, each oxygen is a -2. That's a total of -4. So the carbon's contribution has to be a +4. Sum of the contributions has to equal the charge on the species, and there's no charge on these species, so that has to equal 0. So it went from -2 to +4. Is that an oxidation or a reduction?
-2 to +4. Is that an oxidation?
Okay, good. How did you know?
Because to go from negative to positive, you must have gained electron density.
That's right. It had extra electron density here, and now it has a lack of electron density. That's what that +4 means. So it's giving up electrons, so that's an oxidation. If you look at oxygen gas going to water, or even if you were to look at it in the form of carbon dioxide, here it's 0, and here each oxygen is a 2-. So there's a reduction there. So we can look at the oxidation numbers and see whether it's either electrons are gained or lost. Combustion reactions are an example of oxidation. All right, so this is a combustion reaction, and this is an oxidation. This is a redox reaction. Sorry, this is an oxidation of hexane, but this is really just a redox reaction. This one here is a metathesis reaction. Okay, now we want to determine the oxidation state of the elements in this compound, and none of the non-oxygen containing compounds are peroxides or superoxides. Okay, so the common rules that we know is that hydrogen is +1, oxygen is -2, chlorines, bromines, iodides, those are called halogens. We'll call those X, halogens, right? They're -1 generally. Sometimes they can be different, but generally they're -1. Okay? Monatomic ions are their charge. Or in other words, if it's a calcium ion with a +2 charge, that's the oxidation state. It's a +2. Chloride ion, -1 charge, that's the oxidation state, -1. Okay? Free elements are 0. I think those rules will generally help keep us there, get us there. The sum of all the oxidation numbers has to add up to whatever the charge is on the species. See these species? How many do we got there?
Is that 6?
1, 2, 3, 4, 5, 6 different species here. None of them have charges. all their charges are neutral, so there's a plus 0, right? Minus 0, it's 0. Therefore, the sum of all the oxidation numbers in all the elements has to add up to that 0. So if we look at H3PO4, what do we know?
No, the hydrogen is minus or plus 1.
Each hydrogen is a plus 1, so that contributes a total of plus 3. Plus 3 plus whatever the phosphorus contributes plus whatever the oxygens contribute has to equal the sum of this charge, which is 0. Or the charge on the species, the sum of it equals the charge, which is 0. Oxygen, we have a rule about. Oxygen is a minus 2. Each one is a minus 2, so therefore it contributes a total of minus 8. And so from this, I can see plus 3 minus 8. This needs to be a plus 5 on the phosphorus. So the oxidation numbers, hydrogen is plus 1. Phosphorus plus 5. Oxygen minus 2. These don't add up to 0 because this minus 8 was the contribution to all of the 4 oxygens. And H plus 1 was the individual hydrogen, but the sum of them was given resulted in the plus 3. Okay, good. So the second one, aluminum hydroxide. This is an ionic compound. Aluminum has what kind of a charge?
Plus 3?
And there's 3 of these hydroxide ions, right?
Yeah.
I can see that the aluminum's oxidation number, because it's a simple monatomic ion, is plus 3. The sum of these two oxidation numbers, negative 2, that's from what we said oxygen was, hydrogen plus 1. If you add those together, that equals a negative 1. And that's the charge on that species right there. So the oxygen's negative 2 and the hydrogen is a plus 1. Good. Now, selenium dioxide. So the oxidation number for oxygen is what?
Minus 2.
And there's 2 of them, so it's a contribution of a minus 4. Plus whatever the selenium contributes has to equal, in this case, there's no charge on that species, so it has to equal 0. So it has to be plus 4 for each selenium atom. That's the oxidation number. Okay, good.